Hello, this is Arkasha from MCAT Simplified. Today we're going to be discussing isothermal and adiabatic processes, as well as the forms of the first law of thermodynamics that go along with these processes. The first of these is the isothermal process, which assumes that temperature remains constant. And for a system of ideal gases, which one of the assumptions for gases like these is that there's no intermolecular interactions between the particles, all of the energy of that system, the internal energy of that ideal gas, is in kinetic energy, okay, in the motion of the particles. Since there's no intermolecular forces, there's no potential energy. And as it turns out, temperature and kinetic energy are directly related, where increasing temperature increases the motion of particles, increasing kinetic energy, and vice versa. So, as a consequence, for an ideal gas, if we have an isothermal process ongoing where temperature isn't changing, that means the kinetic energy of that gas isn't changing, and therefore the internal energy is not changing. So for an isothermal process, for an ideal gas, delta U is 0. And we can rewrite the first law for an isothermal process to be that Q, the heat exchange, is equal to W, the work done on or by the system. All right. Now that means that if heat is injected into the system of an ideal gas where Q is positive, normally we would think that would raise the temperature. However, because temperature is constant here, if we inject heat, so Q is positive, then immediately that energy is converted into work done by the system on its surroundings. All right, so heat flows into the system, and immediately that system utilizes that energy to do work on its surroundings, making W positive. Conversely, though, if heat is flowing out of the system to its surroundings, then the surroundings immediately do work on the system, and so W is negative. Okay. And as a consequence, again, the temperature isn't changing as a result. Okay. Now, this is the pressure volume curve for an isothermal process. And just keep in mind that the area under such a curve where you have pressure on the Y and volume on the X, the area under that curve is actually equal to the work done on or by the system. And here, of course, we again denote that for an isothermal system, T is constant. And that means actually, as a consequence for an ideal gas, delta U has to be 0. And the form of the work equation for an isothermal process is given in the following way, where we have N, the number of moles of ideal gas, multiplied by R, the gas constant, multiplied by T, usually in Kelvin, the temperature, which is not changing, multiplied by the natural log of the final volume of that gas, divided by the initial volume of that gas. Now, imagine if the gas is contracting. So VF, the final volume, is less than the initial volume. Well, then this becomes a fraction that is less than 1. And if you take the natural log of such a fraction that's less than 1, the natural log is going to be negative. And so work is negative if the gas is contracting, which remember means that energy is being transferred into that system in the form of work done on that system by its surroundings. Conversely, if VF is greater than VI, so the system of gas is expanding, then natural log of that fraction that's greater than 1 is going to be positive. And so work done is positive. And that means that as the gas expands, it's doing work on its surroundings. Okay? So that's how you would determine the work done if you know the final volume and the initial volume for this ideal gas under isothermal conditions. Next, we're going to talk about the adiabatic process, which assumes that the system in question is thermally isolated such that there can be no heat flow in or out of the system. And so Q is equal to 0. And the form of the first law for any adiabatic process is that delta U, the internal energy change of that system, is equal to negative W. So the internal energy change just only depends on work done on or by the system. But remember that temperature can change in this instance. And so here the temperature, which is related to the internal energy, is going to increase with increasing internal energy if work is being done on the system by the surroundings. And then conversely, it's going to decrease if the system is doing work on its surroundings and its internal energy is decreasing. And here is the curve for an adiabatic process, right? And notice it's very similar to the isothermal curve, which is also depicted here, but a little steeper, all right? Now, we also have some work equations for adiabatic processes. And the first one uses pressure and volume. So if you know the initial and the final pressure and volume, you can calculate work as P1V1 minus P2V2. And all of that is divided by 1 minus gamma. Now, what is gamma? So gamma is actually the ratio of the molar specific heats at constant pressure, which is C sub P of that gas, and the molar specific heat of that gas at constant volume, C sub V, okay? So you would have to know those values to calculate work. You could also calculate work if you know the temperature change, right? So temperature can change here. So work in that instance would be equal to N, the number of moles of gas, multiplied by C sub V, again, the molar specific heat at constant volume, multiplied by T1, the initial temperature, minus T2, the final temperature. And so depending on which values you know, again, if you know temperature change or maybe pressure volume change, you can use either of these equations to calculate that. And that's it for our video on adiabatic and isothermal processes. Check out our website at MCATsimplified.com.